If I were to talk to any random group of Java developers and ask who's happy with ZGC, who's happy with virtual threads, with FFM, JFR, performance improvements, etc., almost everyone would say they're happy. Maybe not with every detail, but they'd be generally happy. But some features involve trade-offs that are more controversial and require some people to give something up. Such trade-offs may be controversial because understanding their nuances requires special expertise, or they require people to take a broader view, that of the entire ecosystem. Now, yesterday, George spoke about seatbelts and jetpacks. The purpose of this talk is to describe the nature of Java's seatbelts and try to explain how they support the jetpacks and how they create value in general. As we'll see, integrity, the umbrella term for Java's primary seatbelt, is at least in part the answer to the most serious and costly problems that software developers face. But before even explaining what integrity is, let's begin with the motivation, how things that have changed in recent memory made seatbelts so much more valuable than before. Java's backward compatibility has been a great success, even though it's not perfect. In fact, I would say it is unmatched by any other programming language when you consider the platform's age and the size of its ecosystem. The Java platform has always maintained its backward compatibility through the Java SE specification, but the careful process of evolving the spec is also applied to supported JDK-specific APIs. The JDK development has a deep-rooted culture to preserve compatibility, and we have the CSR process to track all source, binary, and behavioral compatibility issues. This isn't just a principle that we follow, but a primary source of Java's value. Companies want to protect their investment, and that means two things. Existing code must continue to work, and they don't want to waste effort on rework that produces no business value. But at the same time, they need the platform to evolve to support their own changing needs and new computing capabilities. Now, that's all nice and well, but it's easier said than done. In Java's first decade, like in the first decade of most successful programming languages, maintaining backward compatibility was easy because at first the platform is small and you just add stuff and never remove anything and everyone's happy. But then, partly due to business-related events, Java's evolution slowed down rather dramatically for some years. And then came Java 8, which was a tremendous success, but the pace of evolution hadn't picked up yet to its required level. Now, pretty much from Java's birth, some libraries bypassed the standard APIs and reached for internal JDK packages, classes, methods, and fields. They did it to offer new functionality that was missing from the JDK, or to work around bugs, or to offer better performance for their functionality that they couldn't achieve with the standard APIs. The libraries that did that, and it was primarily libraries, maybe weren't numerous, but they were very popular, sometimes as low-level transitive dependencies of other higher-level libraries. Still, that was technical debt, and the ecosystem was borrowing against its future. But it did work for a while. In the early years, we didn't have the foresight to add strong encapsulation, and the response to libraries reaching for internals was to take extra care when changing those internals. But that approach slowed us down quite considerably. And then it didn't matter because Java experienced some slow years in which the JDK didn't change all that much, either internally or externally. The result was that the ecosystem had ossified around a very specific internal structure of the JDK. The low-level libraries that reach into internals weren't portable. They made the high-level libraries that used them non-portable, and they in turn made a whole lot of applications that used them non-portable. Usually that happened without the knowledge of the application authors. So one option was to give up on making foundational changes forever and just let the platform slowly wane. But that's not what happened. Instead, JDK 9 came along and brought those modules that broke the entire tower of code when they blocked off access to JDK internals and in particular to sundisk unsafe. Now, that's not what happened. Modules were indeed designed to eventually block off access to JDK internals, but that feature wasn't turned on until JDK 16. All runtime access to internals between JDK 9 and JDK 16 remained exactly as it was in 8. Also, unsafe was removed. It is still with us to this day, just as accessible as it was in JDK 8, although that is about to change. So what actually happened was that in JDK 9, Java finally started picking up the pace again. But by then, the structure of the ecosystem had become dependent not on Java's promise of backward compatibility through standard APIs, but on the JDK's internal machinery remaining largely frozen. And then the JDK came out of relative hibernation. The only actual backward compatibility changes that the JDK made in version 9 in terms of the compatibility promise through standard APIs were minuscule. I think about 4 virtually unused methods were removed. The migration difficulty from 8 to 9 or 11 was about 99% due to low-level libraries reaching into JDK internals. So one of the biggest changes is that Java is now evolving quickly, much quicker than before, certainly in recent memory. Internals change frequently. And so reaching beyond the standard APIs to use internals doesn't work, or at least doesn't work for long. Whatever advantages it once brought are now negated by the rework that's required to keep up with the JDK's evolution. And let me tell you that Java ecosystem spent a lot of money on that migration. A recent report estimates the cost of technical debt in general to be quite high. And in this case, the case of Java, it was technical debt that was passed on from low-level libraries to client applications. And maybe the functionality was worth it, but the applications didn't make that choice consciously. They didn't know they were making a deal. Another change is that more and more of the Java runtime is being written in Java. Legacy I/O functionality that used to be written in C was rewritten in Java. Much of the reflection functionality that used to be implemented in the VM in C++ was re-implemented in Java in the core libraries. We now even have a thread scheduler that's written in Java. And the Clara project has produced a JIT compiler written in Java. That was another internal change, but there have also been environmental changes coming from the outside. There are new environments for Java applications that bring their own special requirements. For example, some Java servers now want to scale to 0. And that means they have to start up quickly at or near maximal performance. Finally, the security focus has shifted from defending against untrusted, potentially malicious code, which is actually relatively easy to do in these days of containers and VMs, to defending against vulnerabilities in trusted code. Most attacks on servers exploit accidental vulnerabilities in well-meaning trusted code, which is far more dangerous than untrusted, malicious code. And defending against those is much more challenging. There's one exception, so malicious code is still here, and that is through supply chain attacks, and I'm certain that's something we'll need to address, but we'll leave that for another day. I won't be talking about that today. Now, the value, the business monetary value of security is massive and growing. It's just unbelievable. And as it turns out, there is a strong relationship between integrity and security. Microsoft says that 70% of all security vulnerabilities are due to a lack of memory safety, which is a special case of integrity. In fact, what we call integrity, other people just call safety. So, what is integrity, and how is it related to these different problems, challenges, and changes that I mentioned? So integrity is the promise that some property holds true. And I'm going to define a couple of terms. An invariant is some property of a program that holds true throughout some section of code, which can be the entire program, and that's the case we're mostly concerned with. So we care about invariants that hold for the entire program. Now, I will use the term in this talk, integrity invariant, to mean an invariant that is guaranteed to hold because it is enforced either directly or indirectly by the language or the runtime. And that enforcement is the source of the integrity, and that is what allows making the promise that an invariant holds regardless of what any code in the program does. For example, that no array is accessed outside of its bounds should be an invariant in all C programs. But that property doesn't have integrity. To know whether or not it holds for a particular C program, you need to do a full program analysis, which is usually infeasible. And that is why it is too often the case that this isn't an invariant to C programs. And unfortunately, buffer overflows do occur. On the other hand, allocating a new array in Java at one point in the code comes with a promise that the array will never be accessed out of bounds anywhere else in the code because that invariant has integrity in the Java platform. So integrity allows establishing something locally that is then known to be, in effect, globally, regardless of what code does. Here are some other integrity invariants in the Java platform. Some of them are meant to guarantee that Java programs, unlike C or C++ programs, don't have undefined behavior. They include array bounds checking, no use after free, that the GC guarantees. Java also has runtime type safety, where one type cannot be cast into an unrelated one, and this also avoids some undefined behavior. And these environments are usually grouped under the umbrella of memory safety. But we also have other kinds of integrity invariants, sometimes even surprising ones. For example, that all relative file paths always refer to the same files throughout the lifetime of the process. That is enforced by intentionally not providing a change current directory operation. And when looking at these, it is clear that integrity has been a crucial part of Java's value proposition since the beginning, although it hasn't been called that. Now, these integrity invariants are built into the platform. Most of them are built into the VM itself, or they're enforced by C++ code. But is it possible for Java code, including user code, to establish new invariants that have integrity? Well, we can try. Suppose we want to write a class implementing an even counter of sorts that has the invariant that is important to us. It's a domain invariant, that the counter's value is always even. And we can try to do it like so. So we try to give the invariant integrity to ensure that it holds everywhere without analyzing all the code in the program by making the field storing the value private and by having all public methods preserve the invariant. In this way, if the encapsulation itself, so Java's access control, has integrity, so will our new invariants. So encapsulation allows us to create new invariants and imbue them with integrity. In fact, even the platform's primitive integrity invariants gain their strength from encapsulation. The code that enforces them is encapsulated from other Java code by virtue of the fact that it's written in C++. So before we go further, let's take a short detour and talk about how a Java program is built. So obviously, we have application code. And then, of course, we use a bunch of libraries. And those libraries bring their own library dependencies to form a rather large and deep dependency graph. Now, we said before that an invariant has integrity if it is guaranteed to hold no matter what other code does. And we said that our even classes invariant has integrity if the Java platform's encapsulation has integrity. So does it have integrity? Sadly, no. Each of those libraries in that deep dependency graph that we saw here, even those that we barely know we use, let alone what they do, can choose on its own, unilaterally, to violate Java's access control, and with it, the invariant of the even class. They can use what we call deep reflection, i.e. set accessible to set the value field, or rather they could before JDK 16. They can also do that with some miscon safe or with JNI. Or they can decide to dynamically load an agent that will reconnect into the VM and redefine the class so that the increment by 2 method actually increments by 3. Each one of these mechanisms individually means that Java encapsulation doesn't have integrity, and so neither does that even counter class. To know whether any invariant holds, any invariant that we want to maintain in Java code holds, we need to do a full program analysis, just as we need to do for buffer overflows in C. And it's very hard for an application author to know whether any of the application's transitive dependencies uses any of these mechanisms or not. And of course, whether they do or don't may change with each library upgrade. So it's possible that one of those deep libraries doesn't use, I don't know, JNI, but then you upgrade it, you get a new version, and this one does. And that's why it matters that more of the runtime is being written in Java. So if a JIT compiler is written in Java, Java code could globally change the internals of the JIT compiler and disable array bounds checking everywhere. That if a thread scheduler is written in Java, Java code could globally disable the Java memory model. But the fact that some fourth level dependency could do all that doesn't mean that it would, right? Or would it? So to answer that, we'll need to understand why integrity invariants are important and how and why they get broken. So this is how we started. To evolve the platform at the required pace, we need to be able to fearlessly change all internal code that isn't and has never been subject to backward compatibility. And in this case, the answer to the question of why a library would want to violate other code's encapsulation is that they have various reasons, such as exposing new functionality, working around bugs, improving performance, and these reasons are all justified individually. Every library has a good reason and is sort of right from its own perspective to do it. But the result is a tragedy of the commons. And that was by far the main reason for the difficulties upgrading from 8. And that cost the industry a lot of money. Libraries took on technical debt and foisted it onto unsuspecting, unknowing client applications. Encapsulating internals with integrity so that some private constructor cannot be called by some library will mean that applications don't break again when that constructor is changed or removed. Now, the Java ecosystem wouldn't be what it is without library authors. Their perspective makes complete sense. They do what they do because they need to offer the best functionality to their users. It's just that their individual actions, when taken collectively, in this case, led to a negative outcome that ended up wasting a lot of effort. That's effort by people who didn't know they were taking on that risk. And that's why tragedy of the commons is a tragedy. Every individual action is justifiable, and no single individual is to blame. And if you read about solution to tragedies of the commons, I think the only one that's practical in our situation is regulation. A certain body is in charge of the common resource, and they place rules that they then enforce. Now, let's take a look at security. Suppose that a server has this user session class that allows some sensitive operation to be performed. So this is a security mechanism in a program or a web framework and allows some sensitive operation to be performed only after authorization. And we ensure that by only performing the operation after checking that the user has been authenticated as an authorized user. Now, one thing that's very important in all security mechanisms is that they're robust, by which we mean that their operation is correct regardless of what code in the rest of the application does. And this allows us to treat them as independent code units whose correctness requires analyzing only a small amount of code. Then we can say whether or not they're secure. But no matter how sophisticated the authorization algorithm is, if encapsulation has no integrity, then this security mechanism is not robust. So that superuser field that says I've been authenticated, that could be set with deep reflection or with JNI or with unsafe from any library in the code. The operation itself could be called directly from JNI or deep reflection. And the authorized superuser, the thing that runs the cryptographic algorithm, a library could choose to dynamically load an agent and change it to always return true. But in the evolution case, we could see a reason for a library to violate encapsulation. Surely in this case, no library would feel justified to circumvent a security mechanism. And remember, we're only talking about well-meaning libraries. We're not concerned with malicious code. So the answer is that in this case, even if all code in the application and the libraries is well-intentioned, a malicious remote attacker who is interested in bypassing this security mechanism could manipulate good code to do that. So the application uses a session class, and that's the security mechanism. But it also employs a library. That's called good serializer. And good serializer deserializes JSON. In order to deserialize JSON, good serializer employs a library called neutral encapsulation breaker to instantiate objects without calling their constructors and to assign private fields. Now, there's a bug in good serializer that it doesn't do input sanitation correctly. And that means that an attacker could cause it, in the process of serialization, to deserialize something like that session and write true into the superuser field. Now, who's at fault? The application is innocent. It's doing its best. Good serializer is well-intentioned, but bugs happen, and it doesn't even use unsafe. Neutral encapsulation breaker might use unsafe, but it has no vulnerability in it. So any library that can break encapsulation and any library that uses such a library becomes part of the attack surface area of any code that relies on encapsulation for its integrity. We're back to full code analysis. So it's just important to understand that the integrity of encapsulation is not in itself a security mechanism. In the case we've seen, the security mechanism is built by the application or the framework, that's the session class, together with some cryptographic library in charge of authentication. But if encapsulation had integrity, we could reduce the attack surface area of the session class to some fixed unit of code that is small enough to analyze in isolation. Without it, it doesn't matter how good the session class is or how strong the cryptographic algorithm that does the authentication. All code becomes part of the surface area that we need to analyze, and that's just infeasible. You don't even know if somebody uses a JSON library, and that JSON library could accidentally break your security mechanism. At this point, you may ask, but hang on, you don't need to bust encapsulation to break the session class. Maybe some library writes to the file system, and some vulnerability could allow a remote attacker to directly to manipulate the session class on disk. So shouldn't we also do something about that? And the answer is that this certainly could happen. It does happen. We absolutely must do something about it. Only the best place to do it isn't in the Java platform. The Java platform offers the Java encapsulation mechanism, and so it is in charge of its integrity. But it's not the JDK that provides a file system. The OS does. The OS offers security mechanisms for the file system, and the OS ensures the integrity of those mechanisms. A Java program, just like a program in any other language, must avail itself of the mechanisms offered by the OS to control access to the file system. The OS can do that much more robustly and effectively than the Java platform ever could. Finally, integrity is also important for performance, especially in light of new requirements I mentioned at the beginning of scale to zero and fast startup that's now under the purview of Project Leiden. For example, for some optimization, we want to know whether we can remove some private methods that's not used by some class. So can it be removed? The answer is, in general, no, because maybe a library that I would load uses JNI or deep reflection to access it. So if we had integrity, we could analyze each module individually. And in this context, we go back to our question and ask, why would some library want to bust encapsulation and prevent such an optimization? And in this case, the answer is that it doesn't matter. mechanical transformation that has to preserve the meaning of the program needs absolute certainty about the meaning. That something probably works is simply not good enough. And so we've seen that encapsulation is broken in ways that have significant consequences, either because of individually justified reasons that lead to tragedy of the commons, or unintentionally due to an accidental vulnerability. Plus, mechanical optimizations require absolute certainty that invariants are kept, and high probability isn't enough. So we get this tension where we need integrity, but we also sometimes need to break it in case of emergency. So what kind of balance do we strike? That balance is a vision that we have for the Java platform that we've been working toward for years, and we now call integrity by default. Integrity by default seeks to strengthen the integrity of the Java platform, but it also recognizes that there are situations where people need to opt out of integrity. So the principle of integrity by default is this. All the exceptions to integrity must be explicitly acknowledged by the application in its centralized configuration. And the important point here is that the decision is given to the application. As we've seen, lack of integrity causes a collapse of barriers of sorts, where code can affect other code remotely. And so the decision to allow this or not is given to the owner of the process, the owner of the application, and importantly, not to libraries. If a library really wants to break encapsulation for some reason, the application needs to grant it permission, usually by adding some configuration flag. This means that that fourth level dependency that is upgraded and now wants to use one of those mechanisms will not be able to unilaterally make the application non-portable or perhaps even risk its security without the application's knowledge and consent. Now, what matters isn't so much how the configuration is constructed. Some people say, well, I'll have my build tool automatically add this flag or that flag to grant all permissions, so what's the point? Doing that is fine, because no matter who creates the configuration, in the end, it is an auditable, centralized record that some technical authority can inspect later on and see what risks the application has taken on. So I hope that by now you understand why integrity is important, but you may ask a good question, which is, given that Java didn't start out with strong encapsulation, why not make strong encapsulation opt-in rather than opt-out? The first part of the answer is that we choose to opt out because we can. Strong encapsulation was designed so that its boundaries have a reasonable granularity, and so they're simple enough to configure. Most programs should work with a default policy, meaning 0 flags, or something very close to it, and then enjoy the portability and the other benefits that we mentioned more easily than ever before. And those that don't will be inconvenienced, but not too much. The second part of the answer is that the two regimes, with strong encapsulation or without it, are not symmetrical. The strong encapsulation regime has a lower entropy, meaning that there are fewer hypothetical programs that work in that regime. When you write a new program or do anything, it's best to start in the low entropy regime. And if you have an old code base, you have to expend energy only once to get it to low entropy, and then the barriers are put in place and entropy can't creep in anymore. At least it can't creep in unnoticed. As we've seen, the integrity of encapsulation is of particular importance, and we call that strong encapsulation. Strong encapsulation is not yet airtight, but eventually it will be, and it will ensure that code in one module will not be able to reach into encapsulated components in another module using any of the means I mentioned before, unless the declaring module explicitly allows it in its module info. Code passes its code inside the module, passes its access permissions to other code with a method handles lookup capability object. The application redraws the encapsulation boundaries with add opens or add exports flags. Or the application grants encapsulation busting superpowers, such as the power to redefine classes with agents, say. The most obvious impact that applications feel in the real world is that if they upgrade their JDK from, say, 8 to 11 or 17 or higher, they may need to add some add opens or add exports flags. And some people make the crucial mistake that they think these flags are a sort of a JDK 8 compatibility mode that allows their application to work as they did on 8. And nothing can be further from the truth. The flags cannot possibly make the application work because what breaks it is internal changes, not the flags. An application that uses such flags is an application that will break, and the more flags it uses, the sooner it will break. Rather, the flags are sort of landmine markers. They're meant to keep you alive while you work to clear the landmines. The reaching for internals is a problem, not the flags. And the only fix is to stop relying on internals. Complaining about the flags is like someone who wants to throw a party in a minefield and they complain that the markers are an eyesore. It may seem ironic that rather than the application breaking eventually in some future release, recent JDKs break it with certainty and immediacy by throwing illegal access exceptions. But the key is that we only break the application once and ensure that the only fix is to remove the reliance on internals, and then everything is portable. And once that's done, there are no more flags, the library is portable forever. Now it's protected by backward compatibility. Without this process, the 8 to 9 migration pains would continue forever and ever. A library will just fix a changed internal by depending on another internal. With strong encapsulation, we ensure that we eventually converge, or at least we notice if we don't. So such flags are for temporary use, but if you need a flag to keep some library working, and there's no new version of the library that doesn't require a flag, well, that is a big red flag over the library itself, that it might not be properly maintained, and you should look for alternatives. And that's another benefit of knowing where the problems are. I know of a project that only realized it was dependent on a library that hasn't been maintained in years, was when they noticed they had to add opens to get it to work. So some people may say, oh, well, from your ivory tower, you can try to decree that everyone should fix their technical debt, but in the real world, companies either don't have the resources to do it, or they don't want to direct the resources into paying technical debt. And this is all perfectly true, but the fact that a developer might not be offered the choice to reduce risk doesn't mean that the risk is gone. Sure, some places can't fix their bridges, and from time to time, their bridges do collapse. If you don't upgrade libraries and remove dependence on JDK internals, the risk that the application will break when the JDK is updated is real. So it's best to at least know it's there. And by the way, internals can change in every update, including patch updates. My suggestion would be that if you do add opens and add exports flags temporarily, you at least document why. Either put it as a comment in the script next to the flag or in the Git commit when you make that change. Now, there are situations that, by their very nature, they have to operate beyond encapsulation boundaries, such as unit tests, especially mocking. Some frameworks, they want to maybe initialize some fields in their client code, dependency injection frameworks in particular, application performance monitoring tools, like they have to reach into the internals and see what's going on, and serialization. We have guidance for all these cases on what you should do, and I don't have time to go through it now, but I'll let you know in a moment where to find it. Library authors, when we show them this, they ask us a very practical question. Their library wants to target a range of Java versions. some new API that they want to use may not exist in an old JDK. And in order to compensate for that lack of API, they use internals. But in a newer JDK, internals are blocked. So what should they do? For that, our advice is to adopt the tip and tail model that George mentioned yesterday. We won't discuss it now, but the committers workshop might be a good time to discuss it further. So far, I talked mostly about strong encapsulation, but we're also restricting some aspects of FFM. In fact, we have already. The new foreign function memory API contributed to the JDK by Project Panama. Even though it cannot be used, unlike J9, it cannot be used to break Java encapsulation, at least not easily. Instead, it can lead to undefined behavior, either by calling into code written in a memory unsafe language or by manipulating off-heap memory in arbitrary ways from Java code. Now, this is an excerpt from a recent information sheet by the NSA about memory safety, which, as I said at the beginning, is a kind of integrity invariance. The paper emphasizes the risk of memory unsafety, and it says that even in memory-safe languages like Java, many times you're offered some operations that are either memory unsafe or the language allows calling into libraries written in an unsafe language. And it says that these operations should be localized to identifiable units of code so that those particular units could be given extra scrutiny. The paper further says that this kind of safety sometimes places onerous work on the developer. I don't think that's the case in Java. Most programs don't need memory unsafe operations at all. And we offer those that do a simple mechanism to localize those operations to particular modules. So you can very easily say which libraries are allowed this kind of access. And companies that choose not to heed the NSA's advice can easily put some or all of their code on the class path, and with a single flag, just grant it the privilege of performing memory unsafe operations and or calling native code. That's not recommended, but you have that choice. Achieving integrity by default, which is not exactly where we started has been done in stages. So deep reflection has been restricted by default since JDK 16. Dynamically loaded agents will be restricted. Currently, there's already a warning since JDK 21 or 2. FFM already starts out restricted, but only with a warning. JNI is about to be restricted, started out with a warning. And some safe will be removed almost entirely. But as always, we do this gradually. We emit warnings and give the ecosystem time to adapt. And we have this general process that whenever we add a new restriction, we try to follow this where it makes sense. So something that was previously unrestricted, for example, JNI, we do the following process. So there's a flag. We add a flag. In this case, it's not a new one. It's the same one that's used for FFM to allow people to move from JNI to FFM without changing anything. Called enable native access, and it takes a list of modules and you tell it which modules have native access. And every module that's granted native access, for that module, that native access is legal. Then we add another flag that controls what happens when you do illegal access. So any module that's not on that list. And that flag has 3 levels, which is allow, like anything that's not granted permission still can do it. Warn, which is usually the first default, or deny. And that's the ultimate behavior. Over time, in subsequent releases, the default is gradually increased, and the ability to dial back is gradually removed. So we start at warn, and you're able to dial it back to allow, and then we change the default to deny, and you can dial it back to warn, but not to allow. And in the end, deny is the only possible choice. Another thing we want to do is, in the future, we'd like to add the ability of a module to declare what access it requires. So you write a module that says, I need native access. so that if it's not granted native access, it will be fail fast. It would fail immediately and not at runtime. You can read more about our vision for integrity by default and the practical steps we're taking in these steps. The guidance I mentioned on what to do in circumstances that fundamentally need to break encapsulation, like unit tests, APM, frameworks, is found in that first JEP, or rather JEP draft, called Integrity by Default. And that is all I have. So I think we have 5 minutes for questions.
So you briefly mentioned about safer serialization by just like serializing records, and will there be like a default where like for users to declare that they only want to serialize primitives and records which are known to be safe, or like because other serializations are doing deep reflection?
The future. Okay, so first let me say that the future of serialization is a separate project. There are other people that are best asked that question. For current old serialization, we're making sure that it's also in the document. It shows how people can do it.
Yeah, thank you. And also another question. So about like adding the illegal access flags. So I have seen a common misconception that so if Java developer is making like a user-oriented software and they are packaging via JLink, will these like illegal access flags be added in the JLink packaging so the endpoint customers don't?
So actually, the more important part is not the illegal access, but rather the permission flag. So illegal access is temporary always. It exists for a few releases and then it's gone. It's what happened in JDK 9 too. But all of that configuration, how do you configure the runtime? So we say the command line, but when we say the command line, we don't just mean the command line. Everything that's on the command line could go in configuration files, app files. I don't think everyone knows about them, but configuration files exist. Everything on the command line can be put into them, and those can be shared. JLink, yeah, right, has a plugin that allows you to bake into the runtime image certain flags. And yes, that works. That's another way of doing it. Yet another way is that if you're writing an executable jar, you can put those options in the manifest. Not all of them, but this one you can. And yeah, so these are the options. They're all specified in the respective JEPs.
Thank you very much for the explanation.
Yeah, so I have a question about Java agents. So do you think, like, are you planning to have support to specify the privileges in the Java agent manifest? Because there is no module file for the agent.
Right, so first of all, in order to use a Java agent now, you have to grant permission in the configuration. So you have to say Java agent. So you're already saying, I'm giving you permission to do whatever you like. So if the question is, will we allow someone to say, I want to load an agent, but not give it full permissions. I want to restrict its permissions further. That is something that we're thinking of doing. It's not very high priority.
I was thinking more about JNI. Like we have, like there is Java agent, which is then loading native library.
So in order to,
and
yeah.
I don't want to force the users
so
to.
A Java agent, right, so a Java agent is in the unnamed module. So if you want an agent to use JNI, then you'll need to grant access to the unnamed module, to all unnamed modules rather. Yes, you're right. It's something that would be nice to allow something more restricted.
Hi. How much adoption are you seeing for the tip and tail kind of versioning for libraries? Conversely, how much success are you seeing with libraries adopting your recommendations in regards to unsafe, GNI, etc.?
Okay, so first of all, the second question in regards to unsafe, first of all, they'll have no choice. Just unsafe will be gone. So 100% will follow it. But right now, I was surprised. It's just things that come across our desk. So I was happy to see that Netty has got rid of all its unsafe usage. And that was a big user of unsafe. They're getting rid of 100% of the use of unsafe. With regards to tip and tail, it's not something we track. But I think Spring is Spring Boot is following it. Spring Framework, not yet, but they're getting close. And I don't want to talk too much about tip and tail now, but the trick to tip and tail of making it cheap. That's the trick, because the reason it works better than one size fits all is that it might look expensive, but it's actually quite cheap. And the trick is not to backport much or almost anything. So Spring Framework still backports quite a bit, so I wouldn't call it tip and tail, but I think Spring Boot doesn't. So if you don't backport, you're doing it right. That's like how I would characterize the difference between tip and tail and just doing multi-release trains. But it's not something people report to us, yes, I'm doing tip and tail now. Also, we only gave it that name, I think, this past year. We haven't started evangelizing it. And as George said, it's a suggestion. We think it's a good one. Once you try it, you're going to fall in love. But it's not something that, we're forcing people to do. Anything else?
I'm not sure if you ever heard about a project called Quasar. Quasar? Yeah, I mean your project, which was before Loom. You implemented fibers in
my own project.
Yeah,
Quasar. Yes.
Yeah. So, do I understand correctly that if this policy would be implemented, the project of comparable size and influence would be impossible? Because
no, first of all, I didn't use dynamic agents. I used you had to grant permission, and that was the reason why some people didn't want to use it. But it was very clear they granted permission.
Yeah, you had to grant permission, but
no, you could. What a lot of people do, and I was amazed by this. But they don't. They use agents, but they don't want. They think, and perhaps rightly so, that their users will be scared if they knew they were running agents. So they're going into great lengths to hide that fact from their users. So what they do, they're trying very hard not to ask their users to put Java agents in command line, which is what Quasar did, but to secretly load them dynamically. And that is a thing that is now already emitting warnings. In that project, there was one case where I did access internal fields on the thread class. And for that, you would need to add opens. And there was no option to do it at the time. But today, you could certainly do it. The difference is that the client application would know that this is what the library is doing.
Yeah, but it kind of changes nothing, right? Because if I need to use your library, if I want to have these fibers or whatever, I have to give this at opens. It's not like
at least
really
you know
have a
what
choice.
you're giving up. Because what happened was that in the JDK 8 to 11 or 8 to 9 timeframe, people use all those libraries and they thought, yes, I want to use them. But if they'd known in retrospect that it would cost them so much money later on, they said, okay, maybe we don't need all those libraries. Maybe we need just one. So it's better to have one library. You say, I absolutely need this, that you allow to break something. And then, but if a library breaks encapsulation, that means that the maintainer of that library has to update with every JDK. And then you can test it. So it's much better to have one than 10. So at least you can say, I absolutely need this one, but I don't need all those others. They're not worth the extra effort. So at least the application knows what risk it's taking. Before that, it had no way of knowing. It said, this looks nice, I'm going to use these. Oh, it's going to cost me $3 million later. Is it worth $3 million? I don't know.
That's true. Thank you.
Are we out of time? Or? Yeah, I think we're out of time. Okay, thank you.